Hi, my name is Jack Wardby, and this presentation is on a performance study of epoch-based commit protocols in distributed OLTP databases. This talk is about a paper that was published at SRDS in 2022. This is joint work between myself, Paul Shevlin, and Izzy Matrani from Newcastle University, and Jim Webber from Neo4j. When we want to scale a single node database system, we have two options. The first is to throw more and more expensive hardware at the problem. However, there's a practical limit to how far we can take this approach. An alternative is to scale horizontally, where we partition our data over multiple nodes in a distributed database. And to do that, we need to partition our data across these nodes. So here we have taken our key space A to Z and divided it into three distinct partitions. Now, this approach works really well when we have transactions that access data in a single partition only. So here, for example, transaction 1 accesses data stored on node 1 and he accesses the keys A and B. However, in a practical setting, our transactions might need to access data stored on multiple partitions. For example, here, transaction 2 is accessing key F and key N, which happens to be stored on database node 2 and 3. To ensure atomicity and durability of these distributed transactions, we need to use an atomic commit protocol to get both of these nodes to agree on the outcome of a transaction. To do that, we typically use a protocol known as two-phase commit. So let's have a look at how a distributed transaction is actually managed in practice and how 2PC actually works. So in this example here, we're going to assume the database system is executing two-phase locking. And transaction 1 is going to arrive at node 1, and node 1 is going to coordinate the execution of this transaction. T1 wants to access or wants to read object N, which happens to be stored on node 3. So node 1 ships across the request to read that object. When node 3 receives a request, it requires the necessary locks on that data item, responds to the request, and then we repeat the whole thing again for item F, which happens to be stored on node 2. After the transaction has executed these operations, it decides it's time to commit. So the coordinator for the transaction, which here is node 1, sends out prepare messages to all of the database nodes that have participated in the execution of this distributed transaction. Upon receiving that prepare message, the nodes durably log their response to whether they agree to commit this transaction or not, and send the prepare ACK back to the coordinator node. He then collects these responses, and in this scenario here, we're going to assume that everyone's agreed to commit the transaction. He logs the outcome and then sends the commit messages to all of the participant nodes, and they then release the lock on the data items they've held, send back the commit ACK, and then once the node has received these, he can respond, the coordinator has received these, he can respond to the client with the transaction result. Now, this approach is well established to be a bit of a performance kill in practice. And the reason for this is that we have two sequential network round trips, which are very expensive compared to a single node transaction. Additionally, we also have two multiple sequential durable writes in this execution, and a disk flush, depending on the hardware, can be anywhere between 10 microseconds and 10 milliseconds, which increases the latency of a transaction. And together, these two factors combine to cause higher contention in the database system, because while this whole dance is happening, database locks are being held, which is stopping other transactions who potentially wish to access those data items, which is reducing the concurrency in the system, which then degrades throughput and latency. So this is well established to be a performance killer. So there's been numerous attempts in the literature to mitigate against the negative aspects of two-phase commit. So one approach attempts to minimize the proportion of distributed transactions in the workload. Obviously, the less distributed transactions you have, the more time you have, the less time you actually need to execute two-phase commit. However, it's impossible in practice to avoid distributed transactions completely. So you still have to pay the penalty of executing two-phase commit, which obviously then degrades performance. Other approaches avoid distributed transactions by dynamically repartitioning data on the fly. But this isn't a free lunch, right? Because we have to pay the cost of moving data around in a fault-tolerant manner. So again, no free lunch here. The next set of systems, which are called deterministic databases, avoid 2PC altogether by doing all of the ordering of transactions up front, which means then you no longer need to get the getting users to agree on whether they wish to commit a transaction or not. However, while this approach works well, there are numerous caveats with it. So one of these is, for example, you need to pre-declare your reads and write sets, which in the general case may be infeasible. Another set of protocols attempt to amortize the cost of 2PC by rolling together replication and commitment into one single unified protocol. There is another, and the star of the show today is approach which is known as Epoch-based commit, which does something similar and tries to amortize costs. So let's have a look at what Epoch-based commit actually is. So this idea was proposed in a VLDP paper in 2021. And it's based on the observation that failures are rare and increasingly so on modern hardware, that invoking two-phase commit on a pair transaction basis is actually coordination overkill. So the idea is that rather than executing it on a pair transaction basis, we now execute 2PC over a batch of transactions that have arrived into the system in some time interval we call an epoch. And this allows us to amortize the cost of one round of 2PC over many transactions. So let's have a look at how this would work in practice. So the key thing to note here is we now have this external node, which we call the Epoch coordinator, who is managing the execution of 2PC across the whole database cluster. So as before, transactions arrive at database nodes, they are then processed and committed. So the nodes actually process many transactions in an epoch, but those results are not made durable yet. So the results are not actually released to the client until the end of the epoch and when 2PC is being committed. So here, for example, node 1 is executing some distributed transaction with node 2, and node 2 is node 3, and so on. And after some time, the epoch coordinator decides it's time to commit this epoch. So he sends out the prepare message to all of the database nodes. They then force log a prepared record, which contains the epoch number, all of the transaction IDs executed in the epoch and all of their rights. This is needed for recovery purposes. They then respond with the act of doing this. The coordinator receives all of these messages, decides on the outcome of the epoch. Is this epoch going to commit or going to abort? Logs the record and the epoch number, increments it, and then sends commit to all of the database nodes in the system. They then receive this, and then at this point, they know that the epoch is durable, and they can release the results of all of the transactions they've coordinated within that epoch to the clients. Now, this approach has one key advantage, and that is that we get a higher throughput compared to the conventional approach of executing 2PC per transaction. In fact, we get up to a 4x increase, as was demonstrated in the original VLDP paper. And the kind of general assumption here is, or the general observations, 2PC per transaction is overkill. However, there is some disadvantages, right? There's always a trade-off with these things. So what are the trade-offs here? The first is we are getting increased latency per transaction. Now, this is because let's assume that a transaction arrives at the start of a work interval, at the start of an epoch. We're not releasing the result of that transaction until the end of the epoch. So we're artificially increasing the latency of that transaction because we are waiting before we make that actually durable and can be safely released back to the client. The next thing is this approach, or the epoch-based commit, is really sensitive to imbalanced workloads, right? If we have one database node that's processing a long-running transaction towards the end of an epoch, it can't actually respond to the prepare message with its ACK until it's finished executing this transaction. And in the meantime, it's holding up the commitment of all of the transactions in that epoch. So it's increasing the latency of everything, basically, by just having one long-running transaction on one database node. The next thing to note is that when a database node fails, all of the other transactions executed at all of the other database nodes in the system are also aborted when that database node fails. So we can get an extremely large amount of wasted work that needs to be retried when database node failures occur. So what's our contribution with this paper? The first thing we've done is, it was not really addressed in the original paper, of how do we go about actually determining what is the optimal epoch size for a given system configuration and workload. So our first contribution is we've developed some analytical solutions that allow database administrators to try and determine what the optimal epoch size is for their workload. So there are two analytical models we've derived, both expressed in terms of epoch length and a number of system and load parameters. The first is the maximum, or gives the user the maximum attainable throughput for their system. And this assumes that nodes are never idle. So as soon as they finish executing one transaction, they can immediately begin executing, or there's a request waiting for them to begin straight away executing the next one. The next model gives the epoch length that minimizes the average latency of the system of transactions. And this assumes is a bit different. This assumes that transactions are arriving at some rate into an external queue, so nodes can be busy or idle depending on the rate at which transactions are arriving into the system. And this model actually has two components. It has an upper and a lower bound, which I will touch on more later on. So together, these two analytical models allow a DBA to either choose the epoch length that maximizes throughput or minimizes latency, or allows them to seek a trade-off between the two depending on their application's requirements. Obviously, we make a few assumptions in our modeling, things such as a failed node recovers before another one fails, so we only ever have one failed database node at any time in the system. And we assess the validity of these assumptions through simulations, which again, I will touch on later on in the presentation. And also, for time and space reasons here, I won't go into the nitty-gritty details of the analytical models, but please scan this QR code here and go and check the paper out if you're interested in how we went about deriving these models. So that was contribution one. So what is contribution number two? Well, it is based on this last point here, this assumption that when a node fails, we have to discard all of the work in the epoch. And we think this is a bit overly pessimistic. So we've developed an additional epoch-based protocol, which we call epoch-based multi-commit. So this last point assumes that each node in the database has directly or indirectly accessed that failed node when during some point during the epoch, right? So we've got this information flow between this information dependency between database nodes that is now kind of invalid because it's based on information that was lost. But this is pretty pessimistic, right? Because what happens if a node fails shortly after an epoch begins? Now, it's likely potentially that it hasn't actually maybe processed any distributed transactions yet. And so in that case, it's pretty unlikely that the remaining operative nodes in the system have actually executed a distributed transaction that has used some of the uncommitted data that was held on the node that failed. So this is where multi-commit comes from, which tries to, where possible, avoid aborting all of the transactions in the epoch so we can get potentially, hopefully, a gain in throughput and a reduction in the average latency. So it works by monitoring node interactions in an epoch, which we call epoch dependencies. So what this is actually, if you imagine that we have transaction one that's coordinated by node one, and that happens to require some data stored on node two, then there will now exist an epoch dependency between these two database nodes. There's some information flow between the two of them. So they now can be thought of technically as one unit that needs to fail and commit together. These dependencies can be transitive or direct. So for example, here, if we have transaction one coordinated by node one who updates some item, T2 coordinated by node two can maybe read this item and update some local item on node two. And then transaction three reads this local item created by transaction two on node two. So then we now have this sort of transitive information flow between all three of these database nodes. So if node one crashes, we also now need to abort the other two nodes because there, as I said before, there's this flow of information. So they now need to be thought of as one unit of commit. And this is exactly what the epoch coordinator does, right? It leverages epoch dependencies to create these commit groups, which can then fail independently of each other, because if we have two distinct commit groups, I mean, there's no information flow between them. So if one of those commit groups now needs to abort, the other one can continue without concern. And it does this by creating a undirected graph in which database nodes are represented by vertices and edges are represented by these epoch dependencies. And we can then use connected components to compute these disjoint commit groups, which can, as I said earlier on, can fail independently of each other because there's no data dependency between them. So let's have a look at an example of what this might look like in practice. So as before, we have an epoch coordinator and 3 database nodes. In the work interval here, node 3 has not communicated with nodes 1 or node 2. It's not executed or managed any discrete transactions that have interacted with those 2 nodes, whereas node 1 and node 2 have. So they now have a epoch dependency upon each other. At commit time, the epoch coordinator sends out all the prepare message to all of the nodes, who then, as before, log the necessary information for recovery and respond with a PA prepare ACK. But this time, they piggyback onto this message the dependencies the nodes they've interacted with in that given epoch. So here, for example, node 1 sends, oh, I've interacted with node 2, and node 2 sends the same thing that I've interacted with node 1. The coordinator collects this information and constructs a graph in memory and executes connected components and discovers that, oh, hey, node 1 and node 2 are in a commit group, but node 3 is not. So in this happy path here, everyone's going to commit, so there's no difference. But assume that here that node 3 fails, then we can safely commit nodes 1 and nodes 2 because we know the transactions that they've executed are not dependent on any information that's now been lost. Conversely as well, obviously, if node 3 doesn't fail, but node 2 does, node 1 must abort, and if node 1 fails, node 2 must abort, but node 3 can continue and commit its transactions. So the question that arises here now is, right, like, how useful is this? Would we just not always end up with a single commit group? Would everyone just not interact with everyone indirectly or transitively within an epoch? So we just end up back to epoch-based commit. So to initially investigate this question, we looked at the TPCC workload. And TPCC is, for those who aren't aware, is the canonical OLTP database benchmark, right? And it models a warehouse order processing application. And there are 5 transactions in it, 2 of which are actually distributed transactions, and they access some remote nodes. So in our case study, what we did is we basically simulated this workload for a number of epochs. And obviously for multi-commit to have a benefit, we want multiple commit groups to emerge at the end of an epoch. And when we did our simulation, what we did is we just varied the proportion of distributed transactions in the workload and counted the commit groups that formed. So we simulated 10,000 epochs. We fixed the epoch size to 10 milliseconds, which was the value used in the original VLDB paper. And we assumed a throughput of around 300,000 transactions per second, again, taken from their experiments in the original VLDB paper. And we assumed a cluster size of 64 servers. And what we did is we just counted the commit groups, like I said, and this is what happens here. So we can see that everything, so the red line here is everything after this value is when we only have a single commit group. So we kind of end up with just normal commit. There'd be no difference between multi-commit and the original commit protocol. But everything to the left of this line, we're actually getting quite a few commit groups. So when failures do occur, if we had that proportion of distributed transactions, then great, we could probably save some transactions and not having to retry the whole epoch. So the next thing we did is we wanted to do some performance evaluation, and we did some simulations, right? And the idea here was we wanted to assess the analytical model's accuracy, but also explore the circumstances and build on our initial evidence that multi-commit could be advantageous and potentially outperform epoch-based multi-commit. We want to explore these circumstances. So each simulation took around 12 hours to complete, and this reflected a 100-day operational period, which ensured that we had thousands of cycles with node failures. So for example, when the epoch size was 40 milliseconds, then this resulted in around 11,000 cycles containing failures, or epoch commit cycles containing failures, out of around 200 million cycles. We looked at the following metrics: the system throughput, so the committed transactions per second; the average response time, which was measured as the point at which a transaction enters the system to the point at which it departs, potentially after several retries. We then looked at the committed transactions during failures, which is a really important metric for determining whether multi-commit is giving us any benefit, and this counts the number of transactions committed in cycles when failures occur. And we also looked at the number of commit groups that formed when a given database node failure actually occurred. Just to run through quickly, the parameters in the workload. We had the number of participant nodes. We had this parameter A, which was our epoch length, our work interval, which we varied across our experiments. We had the mean time to commit to be around just below 2 milliseconds. Transaction service rate of a millisecond on average. The mean time between failure of 12 hours. Mean time to repair to be 30 minutes. And we assumed that around 10% of transactions were distributed and that we had an arrival rate of around 30,000 transactions per second. This is the arrival rate of distributed transactions per second. And these are all taken from representative sources in the literature. So go check out the paper and you can see where we've pulled these values from. So in our first experiment, we looked at the maximum throughput. And in the left-hand pane, we have the work interval against the system throughput. Now, the first thing that you probably would observe from this graphic is that the analytical model in red is pretty close to the simulated values of both protocols. And in fact, there's only a maximum difference of 3.8%. So we can conclude that our analytical models are pretty useful in estimating what the system, our maximum throughput analytical model is pretty good at estimating the system throughput. So that validates the assumptions we've made during our modeling. The next thing you'll probably say is, okay, the model actually does identify the value of the work interval that maximizes throughput. But the thing you will also see here is that, in fact, the gain or the increase in the work interval is not matched by the same gain in throughput, right? So here, a DBA may be okay thinking, I can actually minimize or reduce the work interval a little bit and not sacrifice too much throughput in my system. The last thing to note is that the performance of multi-commit and the original protocol here is identical. So this kind of maybe casts a bit of doubt on the utility of epoch-based multi-commit. But the thing to note is that here we're assuming that we have around 10% of transactions are distributed, and we're assuming that there is a paired affinity model, a random affinity model. Now, what this means is that we're accessing at, when we have a distributed transaction, it's just picking one of those nodes, one other node in the system at random. And obviously the other thing as well here is these epochs are quite large, right? This is like a 1.5 second epoch length, which is pretty long time for transactions to interact with each other and form a dependency in one commit group. And this, as you can be seen on the right-hand panel here of the number of commit groups, is that it's always less than one. So we basically never get any sort of gain from having multi-commit here. But in our third experiment, we'll actually look at circumstances in which multi-commit can actually give us some performance gains. But before that, experiment 2 was the average response time experiment. And as before, we've excluded multi-commit from this diagram because it was, again, very similar to the original commit protocol from the reasons I just discussed. But in the green line, we have our minimum bound, and on the blue line, we have our maximum bound from our analytical models. And you can see that the simulation is well within the upper and lower bound estimates, which is good. The next thing to note is that the upper bound actually gives us reasonably accurate in its identification of what is the epoch length that minimizes latency. And here, obviously, it is around 6 milliseconds for this given system. And also, but then also you'll say, well, actually, that might identify the minimum latency, the epoch length that minimizes latency correctly. But the lower bound is actually closer to the simulation than the upper bound. So together, these two estimates kind of can be used in tandem to work out what the optimal is, but also give you a reasonably close estimation of what the minimum latency would be if I selected a given value. So they can be used together to work out, or for a DBA to understand what his latency would be if he chose a certain epoch length. In experiment number 3, we look at the scenarios in which multi-commit can outperform original commit. We call this experiment the paired affinity experiment. So if you remember earlier on, I said that when a distributed transaction is executing, it is basically selecting one other node and in the database cluster at random. Now, in practice, it might be that data, there's underlying correlations in the data, which means that certain nodes are accessed together more frequently. Like, for example, there could be some data stored on nodes 1 and nodes 2, which means any distributed transaction originating at node 1 is more inclined to access data at node 2 than it may be at node 3, for example. And this is what we try to capture in our paired affinity model. So what we've done is in the paired affinity model is pretty contrived example, but it illustrates the point. And it's that distributed transactions access the paired node 90% of the time, and the remaining 10% execute or pick some other node at random to access. And we use the maximum throughput model again. And as you can see here, we actually start to see some difference between multi-commit and the original commit. And now, obviously, on the x-axis, we are varying the work interval from around 10 milliseconds up to 100. And on the y-axis, we have the committed transactions that are saved, or the transactions that are committed when a failure has occurred. Obviously, this is 0 for the original commit, because you always discard all of your transactions. But you can see here in multi-commit, it actually just gain up to, we are getting around 80, we are getting around 80 milliseconds, we are getting over 4,000 additional transactions committed when node failures occur. So this is demonstrating quite clearly that multi-commit can be beneficial depending on the underlying data correlations in the correlations in the underlying data. So it can, as I said, actually avoid a significant number of aborts. So to wrap up, to conclude, we've developed 2 analytical models which allow database administrators to explore the trade-off between throughput and latency. We have validated these models' accuracy through simulations of a 64-node cluster over a 100-day operational period. We developed multi-commit, which helps to minimize transaction aborts when node failures do occur. And we've identified that this protocol actually performs better than the original one when there are underlying correlations in the data, and distributed transactions tend to access specific nodes depending on where that transaction is originating from. Good thing to note here is that it performs identically to the original protocol in all other circumstances. So there's very minimum overhead of tracking epoch dependencies and computing commit groups, because obviously in practice the database cluster maybe would rarely exceed, say, 100 database nodes. So the computational overhead of executing connected components is quite small. So to summarize, in our work here, we have offered an alternative to epoch-based commit and demonstrated how to efficiently tune the parameters of these epoch-based protocols in practical settings. That's all. So thank you very much for listening. If you're interested in knowing more about our work, please contact me on either by email or Twitter or LinkedIn, whatever your preference is. And I'd also like to take this opportunity to plug my podcast, which is called Disseminate, and it's all about computer science research. So please scan the QR code there and go and check that out if you are interested. Thanks again for listening.